Welcome back to ECE 442-542. Happy Engineers Week. Started yesterday, the National Week for Engineers Week. I believe I'm seeing several different dates floating around, but I believe this is National Engineers Week. You need to take pride in your week. Not every discipline gets their own week out of 52. And you do as an engineer, so that's a good thing. During that week, you will be able to work homework number 3, which is due at the end of the week on Friday. And there are Ztransform and region of convergence resources now that I found a book that's online. Actually, it might look something like this when you go to the link, and you can actually access the entire book if you want. But if you go down to chapter 12 or the 12th entry in the table of contents, it's dealing with Ztransforms. And if you open that up or click on that menu, you will be able to find the 6th section of that chapter and read, if you want to, about the region of convergence and how it relates to the Z-transform and the inverse Z-transform if you want additional material. And this book is actually a signal and systems book, and you will find then a lot of other information in there if you want, and you can download the entire PDF if you so desire, but this is then the link to that, and it is on D2L, that link for you to use. That's the resource for the Z-transforms and the region of convergence. There's also discrete equivalent resource under Unit 4, which is where this lecture will reside once it's complete. And those two homework assignments covering Units 3 and 4 will be the topics of Exam 2, which is 2 weeks from Wednesday. Exam 2 is March 11th, and there is now review material on D2L to get you ready for exam number 2. Today what I want to do is quickly review the block diagrams that we introduced last time on discrete equivalents. I want you to keep track of or make sure that you're clear on there's 2 different scenarios or 2 different reasons or 2 different situations for performing discrete equivalents. The first one that we will talk about is the zero-order hold equivalent, and that's when we have a plant that we want to discretize. All the other times that you might want to take an analog transfer function into a digital transfer or discrete time transfer function is the next round, and that includes several different techniques for finding discrete equivalents. A collection of those are numerical integration approaches. Another set are pole zero mapping, and we'll try to get through those prior to exam number 2. That's the idea. In terms of reviewing, this we already looked at, but we're essentially saying, can we go from analog transfer functions, H, C, G, into their discrete equivalents? And that's what I'm saying here in blue on the right, and the 2 different scenarios, and I'll probably get that wrong, so let me just double check. The one scenario concerns those 2, and the other scenario will concern our plants. And I'm trying to indicate those 2 different scenarios so that now if somebody says, find a discrete equivalent, you're not just going to automatically say, oh, I'm going to give him the zero-order hold. You may not want to do that, and there are reasons for that, and hopefully that will be clear after today. You can generate most of these, if not all of them, in MATLAB with the C to D function, as we talked about last time. And the reason we're doing that, again, might be because we want to, maybe somebody's already designed an analog controller for an analog plant and they want to implement it digitally. You're in the blue highlighted scenario. You're wanting to replace C of S with a C of Z. Or maybe they want to do the design and maybe the implementation with a digital controller, and they want to then discretize the plant, make the G of S a G of Z, and that's what I'm indicating in yellow. We're working then with possibly this analog environment, and we're trying to then go between one of these two scenarios. I think the first scenario was blue, and the second scenario was yellow. The first scenario being you might have a filter, you might have a controller, and you want to discretize that. The second scenario is when you have a plant that's preceded by a hold, and the combination of that hold device and the plant is why we are folding it into a hold equivalent, and in this class we'll specialize that to a zero order hold. A zero order hold means we have no more information other than the constant value that we're looking at right now, and we're holding that flat. There's no slope to it, which might constitute a first order hold. We just want a zero order hold, which says hold a value constant during the time, sample time period, and that will become clear in just a minute. Here is our reason number one, as we illustrated last time with this block diagram. We want to create a digital controller from an analog controller, and that might then be being put into potentially an analog system. So we need to sample the air signal. We need to actually change this digital sequence of numbers coming out of our digital controller into an analog waveform, and that's why we have this digital to analog converter. And in this class, we are simply saying, oh, you give me 5, I'm going to hold 5 until the next sample period. At that sample period, maybe your signal says 5.2. You hold 5.2 for that sample period. That's what the hold device, the digital to analog converter, is doing. Then maybe it goes down to 4.8. You hold 4.8. Then it goes to 4.7. You go to 4.7 and hold it for one sample period. The C of Z would just be generating those discrete numbers in a sequence, and your analog plant wouldn't know how to process this chain or this sequence of discrete numbers. It's looking for a continuous time signal. That's why you need this D to A converter. The second reason is when we have a plant and it's now preceded by a D to A, maybe another hold device, and we want to now combine all three of these pieces to generate one discrete controller G of Z. And that's what we're going to concentrate on first, which is what we will talk about today. How do we build or produce this capital G of Z if we're given a G of S and we're told we have a zero order hold that precedes that plant, and a sampler, which is our analog to digital converter, on the output side of that plant. That's what we want to do today, is figure out how do we make that happen. How do we convert? We might have a G of S. That's an electrical circuit. That's an electromechanical system. That's a thermal system. It's some G of S, some mechanical system. We have that transfer function, and now we want to convert it into a G of Z. And once we have a G of Z, then we'll be able to do whatever we want based on this class. But I could ask you, what's the difference equation relationship between the input and the output given g of z? And now you know how to build that, I hope, after exam 1. If I give you a transfer function, capital G of z, and that's relating some input to an output, you should be able to cross-multiply and produce this difference equation that relates the inputs to the outputs. You can do that once you have this capital G of z. Let's then get started. As I said, we are having two different scenarios. We have scenario 1 and scenario 2. Logically, we're going to start with 2. But this is the one that I want to make sure that we are comfortable with. And let's then look at what's happening to this particular process when we are doing this zero-order hold. We have a zero-order hold that takes the digital signal U of z into an analog signal that's compatible with our analog plant, G of s. And the G of s, we want to produce or create an output, Y of s, and that we will sample to produce then this digital sequence of output values that will be Z-transformed to produce Y of z, such that G of z, when all is said and done, allows us to have a relationship that relates the output Z-transform to the input Z-transform, or their ratio. Let's then look at these three pieces. We have the hold, we have the plant, and we have, let's say, the sampler in this block diagram, and we want to now examine each of those three pieces, put them all together so that we know how to produce this capital G of z if somebody gives us a transfer function G of s. And we'll do this actually in sort of maybe the easiest first. Let's look at the output side of these three, which is the analog to digital converter, and then we will look at the hold side, or the input side, which involves this zero-order hold piece. We're looking then at the output side. Suppose, just to give us something to think about, maybe we have some output Y of t that looks like that in the continuous time setting. And we are actually going to sample that every capital T units of time, which I'm exaggerating these. I knew that was going to happen. That's the magic of video. I've now lost my samples, but I can pretty quickly put those back in, I hope. I now have the samples, which I had said were, maybe that's why it stopped. It knew that those were too far apart, but I was just using it to illustrate what I'm doing. You wouldn't want to necessarily be sampling at that large of an interval, capital T, but there's T, 2T. If we go through this analog to digital conversion process, what are you going to see after processing this continuous time waveform through this sampler. What are you going to see in the right-hand side at those, and this just goes on, but I'm only going to illustrate maybe 4 of those points. It's, I hope, clear that this will just generate a sequence of numbers consistent with what it was that we had just sampled. This is now y of little n, capital T. What we're interested in is how do we model this sampler? Meaning, are there any dynamics in going from the left picture to the right picture, which is the process of sampling that analog waveform? Do we have any dynamics that we have to model when we package all 3 of these pieces together? What's happening between the left and the right? We're discretizing the analog waveform. We're just taking a snapshot, aren't we? Are there any dynamics involved in taking that picture at t, 2t, 3t? We're just taking a snapshot and pulling off that number. No dynamics involved. So this is the easy piece. This one we don't have to really worry about in terms of how it impacts our generation or creation of this capital G of Z. We're just every capital T units of time pulling off the particular value of y at that instant. And that will just be y of t, y of 2t, y of 3t, etc. The other one maybe is a little more interesting, which is on the input side. We are, in this class, restricting to the zero-order hold characteristics. Going back to our picture, we are now looking at the leftmost block. And we want to know if we have a sequence of numbers coming in at the input U, we want to produce an analog waveform coming out of that hold device. If I produce a picture, let's say here is time axis, but now on the left in this picture are these instances of time. This is now U of n. Just to give us something to sort of examine, let me generate some fairly random heights on that signal. Now we want to hold those with a zero-order hold, which means don't try to interpolate any information. Just take the given value at the current sampling interval, t or 0, 2t, 3t, and hold it fixed. That means then that on the right here, we will have an analog waveform. It will now be flat. Then we'll go up to this one and it will be flat. So if you wanted to connect those, then you'll go up here and it will be flat. Then we'll go way down here. And these are supposed to be uniform sample periods. And then we have something there. Oh, uniform sample periods. You can make yours look a little bit more uniform than mine are looking. What in the world am I doing? Did I miss one? Okay. I shouldn't have brought it down. That's what's bothering me. Maybe I shouldn't make it as long. We now want to, and this is supposed to be happening at the appropriate instances of time. And what we want to do is figure out, how do we model this behavior? Is it clear what we're doing? You're just going to obtain a sequence of numbers. You'll be handed a number, and you want to then hold that number, numerical value, and create that signal that's then supplying your analog system, whatever is on the output of that zero-order hold. Let's now look at the time response behavior of this process. And I will call this then the time response behavior of the zero-order hold. And to do this, the first thing, let's just look at applying a nominal value. We don't have to worry about a lot of different values. Let's just look at applying a unit pulse to this device that we're calling a zero-order hold. What's the output of that zero-order hold going to look like as a function of time? Here's time. We're applying a value of 1. I'll call this G, sub-zero order hold of T. That's the time domain response of this zero-order hold. And what do we know? If we applied a value of 1, a unit value at time 0, what would happen for the subsequent interval of time, one sample period, capital T? Over that one sample period interval, what's the output look like? It's just 1, isn't it? So this is going to look fairly predictable. There is our zero-order hold response due to a unit pulse. What we now want to do is model that. If you modeled that with, let's say, elementary waveforms, I'm going to call this the unit pulse response of the zero-order hold. How would you model that out of an impulse response, a step response, a sinusoid, a ramp? How would you write that unit pulse response? If it didn't stop at capital T, it could just be a step response, couldn't it? It could be little u of t, where u of t is now our step input, not just a generic input. So this is an overuse of expressions or variables. But if this simply went on and on, you could model that as u of t, as an elementary waveform. But it, pardon? So now it doesn't go on, does it, forever? It stops after capital T units of time, and we can indicate that or represent that by subtracting a similar unit step that starts at capital T, which is u of t minus t, where I think it was clear that that first t was little t, lowercase, and that last t was a capital T. No, it probably wasn't clear, but that was u of little t minus capital T. This is our unit step. And this is our delayed unit step, or a unit step delayed by a time value of capital T. We want to start with, or we are starting with, a capital G of S. That's in the frequency domain. This little g sub ZOH of t is a time domain expression. Let's take that into the frequency domain, because if we have two systems that are cascaded together in the frequency domain, which is what is happening in our block diagram, we can simply multiply those together. We are trying to generate a frequency domain expression for that zero order hold block, and then we can cascade that with our capital G of S that we have available to us, or that's what we're assuming. Let's now take this into the frequency domain. And since it's an analog time domain expression, let's Laplace transform that. And I will go ahead and do the heavy lifting. I will say that that's G sub ZOH of S. I'm looking for partial credit. To give us full credit, you need to produce the right-hand side. What's the Laplace transform of a unit step? 1 over S. Well, that's part of it. And we're subtracting a delayed unit step. Again, I'll do the heavy lifting. I heard unit step, so there must be a 1 over S, but how do we incorporate that delay? That's this scaling factor of e to the minus t times S. This is now the frequency domain Laplace transform representation of the dynamics of that zero order hold. That's G sub ZOH of S. And we can rewrite that by factoring out the 1 over S, and we now have 1 minus e to the minus TS times 1 over S. And if somebody now says, oh, what's the Laplace transform expression of this zero order hold, you could write down that formula. It's now 1 minus e to the minus capital TS 1 over S. Now the unfortunate thing is capital T is some value, and this is generically an irrational expression. That's why you probably never worked too much with this in an earlier class. We always worked with ratios of polynomials of S. And e to the minus capital TS is not represented by a ratio of powers of S. But we're going to be lucky in that this is going to work out nicely, because that e to the minus capital TS represents z to the minus 1 when we go into the digital domain. And that will be a nice operator in the way that we want to be working. Let's now illustrate what we have so far. We have a block diagram. We have G sub ZOH of S. That's the leftmost block. That then feeds our plant, G of S. and then that goes into our analog to digital converter. And that analog to digital converter has no dynamics, so it's not that critical. What we will now look at is how do we start analyzing or creating a capital G of Z based on this combination of the dynamics of the zero order hold and the dynamics of the plant, where I'm going to call that combination the product of 1 minus e to the minus ts over s times G of s. And this is the Laplace transform of the unit pulse response of the system. That is what we would have if we applied that unit pulse for one sample period, capital T. So we're just kind of hitting that system with a pulse, and this is the response that we would see that is produced if our system was modeled by capital G of S. And we can write that another way. We could actually combine that G of S with the S in the denominator so that we could now write capital Y sub 1 of S as 1 minus e to the minus ts times G of S over S. And what's that over S? So if we were cooking breakfast, we would say we want our egg over easy. We want our G of S over S. I don't know, I'm hungry, I'm sorry, that just came to mind. But we are wanting this over S. And what is over S in the time domain? How could you think about that? You're just adding another integrator into this. But you're also preceding that with this 1 minus e to the minus ts. But whatever we start with for our G of S, we want it over S before we start putting it all together to create this y sub 1 of S. And over S just means we're adding an integrator or another S in the denominator of that G of S expression. Now what we want to do is figure out how do we produce the capital G of Z. So let's write this down a few different ways. We have capital Y of S. We could put that into two terms. We have a G of S over S minus an e to the minus ts G of S over S. And what we want to do is actually Z-transform the sampled version of that. And here's what I'm going to do. G of Z, here's how I'm going to write that. I want to take the Z-transform of, here's my notation, and I'll try to explain it in a minute. I'm supposed to be dashing that vertical line. This is script L inverse here's what we're trying to do. We have if that script L inverse of y sub 1 of S, y sub 1 of S is the Laplace transform of our unit pulse response. We want to take that into the time domain. That's what that script L inverse means. We want to inverse Laplace transform that to produce this piece right here is a continuous time signal. These vertical dashed lines are actually trying to symbolically illustrate that this is, we now have a continuous time signal. Let's sample that. with our A to D. That's that rightmost block. Once we've processed that continuous time signal with a sampler, now what's housed outside of those vertical dashed lines and inside the curly braces, which we can Z-transform, is now a discrete time signal. That's really what's going on behind the scenes. We want to figure out or get an expression for capital Y sub 1 of S. We want to take that into the time domain, sample that, which really means replace little t with little n capital T, just chop that expression up, and then Z-transform that sequence of numbers. And you know how to Z-transform a sequence of numbers. That's going to be kind of messy to always write down, so I'm simply going to say that when I do the following, if I want g of z, I'm going to say that I'm going to simply define that to be the Z-transform of y sub 1 of s. So my g of z, when I'm doing a zero-order hold equivalent, is going to be defined to mean this script z of curly brace capital Y sub 1 of s in curly brace is actually what I'm doing right above. Is I'm taking all that's inside into the time domain, I'm sampling it, and then I'm Z-transforming that discrete sequence of numbers. But that then actually becomes, if we go back up here, just the Z-transform of two different pieces. A G of S over S and a G of S over S delayed by capital T units of time. So I'll write that as the Z-transform of G of S over S minus the Z-transform of e to the minus TS G of S over S. Now we can invoke what we know e to the minus capital TS represents in the Z domain. Since it's going to be Z-transformed, e to the minus capital TS is the Laplace transform of a delay of capital T seconds. And we now, or you've already told me, that the Z-transform of a capital T second delay can be written in terms of Z as Z to the minus 1. And that now allows us actually to simplify this expression for capital G of Z. It's made up of two pieces, G of S over S and G of S over S delayed by one sample period. And we are going to be able to factor out that one sample period by simply scaling it or pre-multiplying it by Z to the minus 1. We now can say that G of Z is this Z-transform of G of S over S, just introduce another pole at the origin in G of S, minus Z to the minus 1 Z-transform of g of s over s. But we just calculated g of s over s, or its Z-transform. So let's not duplicate that. Let's just factor it out. We now have 1 minus z to the minus 1 Z-transform of g of s over s gives us our g of z. And that 1 minus z to the minus 1, that can be just a ratio of z's. That's just an expression involving z or z inverse, depending on how you write it. That's what we want. So we've just derived the expression, or the way to compute the zero-order hold equivalent of a particular expression, capital G of s. And you might see this referred to in some sources as the pulse response transfer function, which is what we use to excite that system. We excited it with a pulse, and that now can be written as g of z is 1 minus z to the minus 1 Z-transform of g of s over s. And what I want you to do between now and exam 2 is get very comfortable with making this computation, or performing, or finding these g of z's, these zero-order hold equivalents. To do that, to get you started, to get us kind of, we aren't even going to jog initially, let's just crawl. Let's do this for a very simple g of s and see what happens. Let's try to find a g of z for a very simple g of s. And we'll do more than just crawl, hopefully. So I'll say examples of zero-order hold equivalents. Example 1. Like I said, we were going to crawl. What do you think we're going to use to crawl? What do you think we'll use for capital G of s? There's no wrong answer. It just may not be consistent with what I've picked. What would be a very simple G of s? S, 1 over s. 1, that's even simpler, isn't it? Why go with 1 over s when we can just go with 1? I'll make it just a little more challenging. I'll make it a 5. But that's the same as 1, isn't it? Just scale. But I want you to see maybe where the value comes into play. So this is just a gain. If somebody had a system that was just a gain in the analog setting, what would that look like when you found the zero-order hold equivalent, or what might be called the pulse response transfer function of a gain? Pictorially, you could express that as this zero-order hold G of s, which in this example is just equal to a number, 5. That just scales what's coming in at the input by a factor of 5, and it goes through this A to D and creates this output. All of this will be what we will call G of z, which is this zero-order hold equivalent of a gain. Or the pulse response transfer function of a gain. We know what the expression is. That's 1 minus z to the minus 1 of the Z transform of the plant or the system G of S over S. But we now know what G of S is. We've picked a particular one. This is now 1 minus Z to the minus 1 Z transform of 5 over S. Now let's go ahead and work our way through this more in as many steps as maybe it takes to go through each step. The 5, our gain, that's just a constant. That can factor out of the Z transform operation. That's scaling every term in our Z transform. Let's pull that out front. And remember what we said we were doing with, well, maybe I'm not doing it completely, but this is what we're doing if we don't have a table of Z transforms. We would now take this into the time domain. What's 1 over S in the time domain? That's just the unit step, isn't it? So that looks like 1, doesn't it? We now sample that. And what happens when we sample a constant 1? That's the unit pulse, isn't it? That we are, or the unit step response in discrete time. So we will now say this is going to be 5 times 1 minus Z to the minus 1 Z transform of this 1 over S, which is this unit step. And if we, I don't have it, but you have it either, and I'm actually giving you another Z transform table under the heading of exam 2 material that has multiple columns. It has a column that has the time domain expression, it has the Laplace transform of that time domain, and then it has the corresponding Z transform of that S domain expression. That's under exam number 2 material, and you could now look up that 1 over S and find it. If you use the old table, this would be, I believe, row number 6 in the Z transform table. For exam number 1. And what did the unit step look like in terms of the Z transform? Or maybe what I should do is, before I get there, let's now rewrite that Z to the minus 1 as 1 over Z. That's the same thing. But now down here I can put all of that over, those two terms over a common denominator, which is Z. And what's this piece? If you go into row number 6 and find the Z transform, do you remember what that is? Or that's 1 over 1 minus Z inverse, and if we clean all the Z inverses up, that becomes Z over Z minus 1. That's what this piece is. Wow. So what happens? We find that the zero order hold equivalent of a gain is a gain. And it's the same gain, which makes sense, I hope. If I gave that to you on an exam, again, that would be a very big gift. If I said, find the zero order hold equivalent of a gain, you could write G of Z equals that gain, couldn't you? Now, let's do it. Let's start walking. That was crawling, but you, I hope, saw the process. Suppose that now somebody says, suppose we have this zero order hold in front of or precedes a pure mass system. What I'm meaning in a block diagram sense is we have this zero order hold and our system is this G of S corresponding to a pure mass, and what we want is to find capital G of Z. We found what it was when capital G of S was a gain. We put all of those things together and out fell a gain. Now I don't think it's going to fall out quite so simply. Do you remember what the transfer function of a pure gain is? G of S. And if you don't, you go back to your physics. Now everybody's nervous, right? But remember our free body diagram. Here's another free system. There's our mass. It's just free. And it's floating on, let's say, in a hockey rink. So there's no friction. We can just push it. We can apply a force, and now we want to see how it evolves dynamically. We have this force, let's say, applied here, we'll call U, and that's not the unit step. That's just a generic input U of T. This is our force input. Do you see how I'm overusing U? Not YOU, but the letter U. Just to be clear, okay? There's our force input. Let's say this is where we've drawn a line in the sand or on the ice rink and said, here is 0, here's our origin, and we want to know what is capital G of S. How could you make Newton proud? What is going on if you now have a mass and a force? F is equal to ma. And what is A in terms of the variables that we've described here? X is the position, A is acceleration. We just differentiate that position a couple of times and we have F is equal to ma. F is U, U of T. So from physics we have our force is equal to mass, m, times acceleration. That's from physics. And we might actually want to write that in terms of powers of the derivatives of our position. So we might rewrite that in terms of x double dot of t, and we can do that by dividing both sides by capital M, so that we now have 1 over m u of t. And just to introduce more variables, I don't like 1 over m. Let's just call that a u of t. But this is simply a constant a is 1 over m. We now have a second-order differential equation. And we want, that's in the time domain, we wanted a capital G of s. What do we do if we want capital G of s if we have a differential equation? We simply Laplace transform. And if we're looking at the transfer function, we don't have to worry about initial conditions. It's getting even easier, isn't it? We're barely walking, but we're walking versus crawling. Now let's Laplace transform. X double dot is equal to AU. We want a transfer function. What's the left-hand side look like if we Laplace transform the second derivative? Each derivative gives rise to what in the frequency domain? An s. And we have two of those. So now we have s squared, and we're taking little x of t into the frequency domain, so we'll replace that with capital X of s. And the right-hand side is so easy, it's hard. The a is a constant. That factors out of the Laplace transform. We have the Laplace transform of little u of t, which is some generic input. We don't know what it is, but we do know that that will just be called capital U of s. This now allows us to solve for capital X of s, which is the Laplace transform of the position of that pure mass. That is now a over s squared u of s. And our plant now, a pure mass plant, a pure mass system, capital G of s is a, where a was 1 over m, divided by s squared. Capital G of s is a over s squared. What was our G of s when it was just a constant? It was just 5, wasn't it? G of s was 5. Now it's become a over s squared, so it is a little bit more interesting, a little bit more involved. Let's now find the zero-order Hult equivalent of this pure mass, or of this G of s. Or you could think of this as the zero-order Hult of two integrators, a double integrator. That's what it is. A pure mass looks like two integrators. We don't have any damping. We don't have any spring constants. We just have a pure mass on a hockey. What do you call a hockey? It's not a field. Rink, thank you. Tells you how much I play hockey. All right? So on the hockey rink, here's our pure mass. G of z is what we want. That's 1 minus z to the minus 1 Ztransform of G of s over s. This is now 1 minus z to the minus 1 z transform of a over s cubed over s, s squared over s, which is s cubed. Whew. S cubed. Do you remember what that looks like when we take it into the time domain? What's 1 over s look like? So let's just work our way up. 1 over s when we inverse Laplace is 1, isn't it? We're viewing this like a signal. 1 over s is a unit step. We take it into the time domain, it's 1. 1 over s squared. Now you're integrating a constant. What happens when you integrate a constant? It's now a ramp, isn't it? The area is just growing and growing. Now we're integrating a ramp. You integrate t, what do you get? T squared. And here you have to keep track of a constant, basically, but you get t squared over 2 factorial. That's the structure of what happens in the time domain. Now we have this parabolic increase in time. If we took this into the time domain, we want to sample that and then Z-transform those sampled values. But we can go into the table and say that, well, we can now find the Z-transform of something over S cubed. And if you go into the Z-transform table that you used for exam number 1, it's going to be on row number 8, 2 rows down from the previous one, which was 1 over s. So it was 1 over s was row 6, 1 over s squared was row 7, 1 over s cubed is row 8. And what you will find is probably not these constants, so we have to keep track of those. We have an a over 2 factorial, or just 2, so let me get rid of the factorial, since that's 2 times 1. And what happens when we z-transform 1 over s cubed, we get t squared z plus 1 over z minus 1 cubed. I told you it gets a little more interesting. But what happens with this 1 minus z to the minus 1? We can rewrite that as z minus 1 over z. We have an a over 2, and here we have t squared z plus 1 over z minus 1 cubed. Now we can clean things up a little bit. This z minus 1 factor will eliminate one of the z minus 1 factors in the bottom that was cubed. The z downstairs in the front can cancel that z upstairs. And now we have our zero order hold equivalent of a pure mass, a hockey puck in a hockey rink. I remembered. I forgot before, but you helped me recover. We have AT squared over 2. That's just a constant once we know the mass. The mass is 1 over m. That replaces little a. T is our sample period. We have to pick a sample period. And now we have z plus 1 over z minus 1 squared. That's the zero order hold equivalent of a pure mass. What if we let's put some numbers in here. Suppose we let the mass be 1 kilogram. A was the reciprocal of that, so A becomes 1. And suppose that we get real creative with our sample period and we let that be 1 second. Now what's G of Z look like? We now have 1 times 1 over 2, or 1/2, Z plus 1 over Z minus 1, quantity squared. What's that look like in the Z-plane if we now sketched the pole zero diagram of that system represented by G of Z? What did our pure mass look like in the S-plane? Just for something to connect with. Our pure mass was A over S squared, and we set A equal to 1. What's the S-plane pole zero diagram look like for a pure mass? 1 over S squared. Where are zeros? Finite zeros. We don't have any finite zeros, do we? We have 2 zeros at infinity if we wanted to talk about that, but we just say we don't have any finite values of S in the numerator that causes that G of S to vanish. We have no zeros. Do we have any poles? We have 1 over S squared. We have 2 poles at the origin. What do we have here in the Z-plane? Do we have any zeros? Do we have any finite zeros? Any finite values of Z that cause capital G of Z to equal 1? I'm sorry, to equal 0. I think I fell on the ice rink and hit my head, because I need to over easy. I'm sorry, over S. Probably have dessert before I have my over S. What do we have? Where's our 0? Do we have a finite 0? It's at -1, isn't it? This isn't hard. Do we have any finite poles? Let me just put some tick marks on the diagram. Those are points representative of the unit circle. Do we have any poles, finite poles, in this zero-order hole equivalent of a pure mass? Values of Z that cause the denominator to vanish. We have 2 such poles, don't we, or values of Z. We have 2 poles at Z equal to 1. So I'm going to illustrate that by 2 x's. They would be exactly on top of each other, right at 1. And is that consistent with where our poles were in the S-plane? And remember the relationship that relates Z's and S's. Our poles in the S-plane were at the origin, weren't they? When S was equal to 0. E to the 0 says Z is equal to 1. That point at 1 on the unit circle is where we find our frequency response in the Z-plane, consistent with the imaginary axis in the S-plane, and the origin in the S-plane, S equals 0, is similar to this point at Z equal to 1. That's a little different than what's our pole zero diagram of a pure gain look like? The first example. Where were our zeros? Where were our poles? We didn't have any, did we? This is a little bit more interesting. We now have two poles at the origin, and what's that 0 at -1? Well, that's kind of like infinity. That's about as far as we can go on the frequency when we walk around the unit circle. We can only go to -1 in frequencies when we have sampled something. Let's look at one more. We've looked at the zero order hold of a constant. We've looked at the zero order hold of a pure mass. This one was 5. This one was 1 over s squared. Why don't we look at something in between? Let's look at a pure integrator. 1 over s squared was 2 integrators. What happens when we look at the zero order hold of an integrator? Maybe we jogged before we walked. Let's walk with this integrator. What's g of s look like? If I said, give me the frequency domain expression for a pure integrator, maybe with a gain, k, what would you say? That's just k over s, isn't it? All right, let's find g of z. We know how to do that. G of z is now 1 minus z to the -1, Ztransform of k of s over s. We just add another s in the denominator. This is now k over s squared. This is now 1 minus z to the -1. We now had the table out. We looked at table row 6. We looked at row 8. Now we go between and we look at row number 7, and we find that the Z-transform of a 1 over s with a k in there is k capital T z over z minus 1 squared. You need to go home and make sure that you're comfortable with where these are coming from. This is not magic, it's from the table, but next time I think we might derive that expression. Where did that table entry come from? How did we go from 1 over s squared to tz over z minus 1 squared? Where did that come from? We'll do that next time, but now let's finish this one up. We now have 1 minus z to the -1 is z minus 1 over z. We have k tz over z minus 1 squared. One of those z minus 1 factors gets canceled. The z gets canceled. And now our g of z, our zero order hold equivalent of a pure integrator with a gain of k, becomes kt over z minus 1. What's that look like in terms of a pole zero diagram? Do we have any finite zeros? I heard a yes, I heard a no. Do I average those? No, I get out my yes-no coin again, don't I? And I flip it. And what's it going to land on? Do I have any zeros? Finite. I have an infinite zero, don't I? But I don't have any finite zeros. Do I have any finite poles? And is that consistent with where you would think